Good afternoon, ladies and gentlemen. This is Module 6. I'm going to go through some exercises that we've designed to keep everybody amused today. I hope you enjoy it. The scope of the presentation, I'm doing exercises for the Ashtone design method and also the TRL SADC SADC design method. I don't think there's time for any more than that, but I do have a spare as well in case we we have a bit more time. But at the moment, this is the scale of what I'm going to do. Preliminary. Step 1 for all design methods is to calculate the design traffic. That requires a traffic count, a knowledge of the traffic growth rate, details of the axle load, so the axle load damage can be calculated, and the design life. Now, normally when we do exercises, we've got half a day or even more. So we would actually combine this as part of the exercise. But I'm assuming that you can all do this, and we're assuming for these exercises today that this step has been completed. So we know the traffic, we know the design life, and we can get on with the actual engineering. Okay, we're going to do 2 exercises in this session. The first exercise is 2 roads, A and B, and we're going to design them based on the Ashtone design method and also the TRL SADC design method. And the second exercise, we're going to design a completely different road using the DCP-DN method. The first exercise, the old road between Low Lake and High Lake is to be replaced. The expected traffic over the 15-year design period is 1 million equivalent standard axles. There are 2 alternative routes. The most direct route, Route A, is 10 kilometers long, but passes over very soft soils. The alternative, Route B, is 12.5 kilometers long, but passes across relatively strong soils. The geometric alignment standards are likely to be similar because the terrain is very similar. The question is, which route will be the least expensive to build? And that will almost certainly depend on the structural designs that we can come up with. Exercise 2, I mentioned now, but we will come to this after the exercise 1. You are required to design a new road, which we'll call Road C, on virgin ground to carry traffic of 0.1 million equivalent standard axles using the DCP-DN method. The road is in a fairly wet climate. Available are 2 gravel materials, one of DN, DCP number 3.5, and another of DN 10.0, and these have been determined in the soak state. The 20th percentile DN value of the existing subgrade is 18 millimeters per blow up to a depth of 600 millimeters. So we're going to put our road using these materials, we hope, if they're satisfactory, on top of this subgrade. But we'll do that at the end of after we've done exercise 1. Exercise 1, returning to it, the first task and the basis of the exercise is to carry out the structural design of both roads. The preferred structural type for such a road consists of a double surface dressing, a road base of natural gravel, typically with a CBR of around 65%, and a sub base of relatively good quality natural gravel with a CBR of somewhere around 30%. And we can make up the rest of the structure with the sub base, assuming that the rest of the road is satisfactory. So we will first of all use the Ashtone method. You carry out, or somebody carries out, a soil survey by investigating the strength of the subgrades under existing connecting roads at the wettest time of the year. Obviously, this road has been there for this route has been there some time. We're going to put a new road in, but there are other roads in the vicinity on the same subgrade. Got these results, 10 readings. Route A, this is the in situ CBR measured along the alignment in 10 different chainages, and Route B the same. So that is the data that we're going to be working with. We're going to carry out the structural design to start with based on the Ashtone method. And if you recall the road notes in the previous lecture, we have to define the change in present serviceability index. In other words, how much deterioration can we tolerate before we have to repair or rehabilitate the road. That I've set to 2.7. You'll see why in a moment. We have to set something that was called the reliability, and that is defined by this factor Z, which goes into the equation. And for 90% reliability, that is less than or 10%, a small chance of 10% that it won't quite reach the design traffic level, but 90% probability that it will. So that's a reasonably safe reliability level. Some people would choose a lower value for low volume roads, but for this particular example, we'll choose 90%. There's the term that we call variability, S0. This we've set to 0.4. This covers all the variability associated with road design, including variability in the traffic levels that, and obviously never certain, they can go up or down. They can be higher or lower than our estimates, plus the variability in performance, which is also partly taken into account by the reliability factor. We also have to choose the drainage factors. I don't think I said so, but the area of this road is relatively moderate climate. It's not a severe climate, so we're choosing 1.0 for the drainage factors. If you remember the lecture, if the weather is poor, we have severe storms, we can increase the value of the drainage factors, and that will give us a thicker pavement. And the traffic level, as we've said earlier, is 1 million standard axles. Now, what I've asked you to do as the designer, I've asked you to prepare two designs, one based on the average subgrade strength for the year, and one based on the lower percentile subgrade strength. In fact, the Ashtone method requires quite a complicated weighting factor, but hardly anyone I know ever uses that. We either take the 20th percentile or average, depending on what the climatic conditions are. So we'll do both to see what happens. We therefore need the average over the year and the lowest 20 percentile. If we use the lowest 20 percentile, that will reduce the risk of poor performance, as will the reliability factor and the variability factor. But these are why calibration is strongly recommended before anybody actually adopts the Ashtone method permanently. And you would do that calibration based on performance of your own road network. We need to draw, well, how do we get the 20th percentile? There are several ways. The way I like to do it is to draw what we call the cumulative percentage distribution. That's essentially the statistics from that data. Those of you that are familiar with statistics will know that the 90th percentile can be obtained from the average value minus I think it's 1.4 times the standard deviation. But I think the best way to do it is to draw the cumulative percentage. So if you look at the next slide, what we first have to do is order those from the lowest to the highest. So chain is 1, the CBR was 5, but the lowest value in the 10 is 3.8. So 3.8 is top of the next column, going right down to the maximum value at 6 at the bottom. We then have to work out what the percentage is. Well, there's only one reading for each chainage, so each one is effectively 10% of the total. And in the right-hand column, we calculate the cumulative percentage. So after one reading, it's 10%. After two readings, it's 20, right up to 100. And we plot the cumulative percentage against the CBR. And this is the graph we get. The left-hand axis is the cumulative percentage, obviously ending at 100, and the x-axis is the CBR. Now, this is an entirely fictitious result. In practice, this would not be a fairly good straight line. It would be much more of an S-shaped curve. and you would pick off the 20% level. And as you can see, it's about 4. So that's route A. The same thing for route B. This is stronger, as you know, and the 20th percentile can be read off the graph. Well, nearly read off the graph. It's actually about 9. In fact, it's actually 9.0 if you calculate it properly. But that's what the cumulative distribution looks like. Again, as I say, it would normally be an S-shaped curve. So these are the results we've obtained. Road A, the 20th percentile CBR is 4. The average CBR is 5. And we have to convert those, if you remember, into modulus values. Again, remembering that the Ashtone design equation is based on imperial units, not metric units. And so the modulus has to be in terms of pounds per square inch. And if you remember the notes we gave before, the value of the modulus is 1,500 times the CBR approximately. So that's where those modulus values have come from. Now we go back to the Ashtone method in general. What we're going to do is use the Ashtone equation. If you remember, if we set the PSI change to 2.7, it is actually an equation with 3 variables or 4 variables in it, and you cannot solve it for the traffic. Well, normally it's a relationship between the traffic and the other variables. So the easiest way to obtain the structural number is to put different structural numbers in, calculate the traffic until you get to the traffic level that you want. So that's what I've done here. Obviously, you can program the equation into your spreadsheet and do it yourself really quite quickly. As I say, there's only those 4 variables that we've discussed already, so it's quite easy to do. And if you do it, you'll find that these are the results we get for road A using the 20th percentile CBR. We get a structural number of 3.4. If we use the average CBR, we get a structural number of 3.2. For road B, which as you know is stronger, the required structural number is 2.6 or 2.4, considerably lower than for road A. This requires the CBR values in the soaked condition as required by the TRL-SADC method. This does not mean that we believe that the road will have soaked CBRs in its operating condition, but it's a simple way of actually identifying the qualities of the individual subgrades. The values we would use in this example are shown in the next slide. There you can see that the third row down, the soaked TRL-SADC CBR is 3. This compares with the 20th percentile and the average. So obviously the soak value is the lowest. And if you go into the design chart in the road note, you'll find that for moderate or good conditions, climatic conditions, as opposed to severe conditions, you require a structural number of 2.15. And in the wet climate conditions, you need a slightly higher structural number of 2.35 for road A. For road B, again, the soak value is 6. And if you look in the chart, for dry moderate conditions, you require a structural number of 1.85 or 2.08 in the wet climate. And as you can see, compared with the Ashtone values, these are quite a lot lower. The Ashtone designs are significantly thicker, but could be less if some of the assumptions that we made concerning the drainage factors, which we set at 1, the terminal serviceability level, which we limited to 2.7, we could allow the roads to deteriorate further before we determine that they have failed or finished their design life. The reliability level can be reduced, as I said earlier. For low volume roads, that's often set at 80% rather than 90, because we can tolerate slightly less good performance compared with the higher traffic roads. But this is not entirely satisfactory. It means that we have to calibrate the Ashtone method, And there are a number of issues about that which we can discuss later if you wish. Primarily, I think to sort of whet your appetite, the structural numbers that come out of the Ashtone method are, as we've said, a little bit higher than we would like, but the relationship in that equation, if you remember the equation, the traffic was related to the structural number raised to the power 9.36. Now, all our experimental data indicates that that is really quite a high value. And if we do calibrate the Ashtone method, it would be, for example, a good idea to use a relationship there which we have developed from our own studies. And that would give you not a structural number depending on such a high power, but on a slightly lower power, which would match the data that we've got available from studies we've done in many parts of the world. So calibrating the Ashtone method. But the Ashtone method is very good because of its use of reliability, the fact you can change the terminal serviceability level, and so on. So it's a very versatile method. So how do we get our 1.85 structural number? Well, we've said already that we need a reasonably good quality natural gravel, and we have some material of CBR 60. We also have some natural gravel of CBR 30. So these are ideal for the road base and sub base. And that is a typical design that will carry our traffic quite happily, I believe, for the 15 years as per the design. So that is the end of exercise 1. A reminder of exercise 2. We are going to design a new road, road C, on virgin ground to carry 0.1 million equivalent standard axles using the DCP-DN method. The road is in a wet climatic area. The available gravels, one has a DN of 3.5 and another DN of 10 determined in the soaked state, which is what we need to do for that particular climate. The 20th percentile DN value of the existing subgrade is 18 millimeters per blow, up to a depth of 600 millimeters. So if we use the DCP-DN method and look at the chart, you can see that if we use the better gravel, which has a DN 3.5 and use 150 millimeters, use the other gravel, which has a DN of 10. If you look at the chart, you'll see that the limit for that should have been less than 9, but we have to exert some engineering judgment here. It's not far off the specification, and we have a relatively adequate subgrade beneath it of 500 millimeters for the DN per blow of 18.0. And if you check the overall DSN 800 of that structure, you'll find that it is greater than the specified minimum of 73. So basically, although the natural gravel subbase is not quite up to spec, the overall structure we believe is fine. So thank you for working through these. I hope you enjoyed it. Goodbye for now.